So let's get started. Last lecture we actually talked about visualization. Today I'm going to talk about optimization techniques, but before we get started on that, I wanted Cemil to show you the work he did last semester on visualization, in particular neural style transfer. But I don't know if that's exactly visualization, but it's a related topic. So neural style transfer is the process of taking a taking the content of one image and taking the style of another image and combining the content and the style to get a third image. So you can typically get a photograph and a Van Gogh painting, and then basically see that photograph in that style. So Cemil has 5 minutes to explain to you how this is done.
Okay, I will talk about how we can do that. First, we should obtain the content and style representation of an image. First, I will talk about content. The content actually is pretty simple. You just pick a layer from your CNN network, from your deep network, and the filter activations at that layer becomes your content representation. So our aim is to match the content representation of the output image with the content representation of the input image, but the photograph image.
What do you mean by filter activation?
Filter activations, for example, take ReLU, output of ReLU 4, for example, your fourth ReLU, is there are activations. If you have 40 filters, you get 40 matrices. So you use that tensor as features.
Yeah, so the last activation function.
No, not last. You pick.
The one that
You choose.
activation function.
But the style is a little bit tricky. You don't use the activations directly, but rather you compute cross correlations of the filter activations. And the reason why we do that is the style should be should be present in all filters, in most of the filters. So if you want to capture the style, you can just take cross correlation of the filter activations and see what common thing is there. The loss function is very simple. You just take mean squared error. Actually, there is a third thing here is total variation loss. It just makes the output image smoother. I used Adam, but you use other optimization algorithms as well. But how do you generate the output images? You first start with, you have 3 images, one content image, one style image, and one noise. Basically, you start with noise, and gradually, using backpropagation, you generate the output image you desire. How you do that? You define a loss function. This is the loss function, and you try to minimize that. After each iteration, the noise becomes more and more like a real image, and after, let's say, 300 iterations, you get the final result.
Is the sum of alpha and beta like 1 or something?
Alpha, yeah, it's 1. I chose that one.
Mm-hmm.
But you can change that. For example, if you want more realistic image, more content, you can increase alpha.
Does it like is it kind of linear? Like
Yeah, linear combination.
okay.
Okay. Here's an example result, and here's another result. And now we will make a live demo.
So this is a notebook from the KNetML GitHub organization. So you can go to github.com KNetML, and the neural style transfer repo includes a complete notebook on how this is calculated with code that actually works. Are you going to run it?
Yeah, it's
start with noise image?
Yeah. You have two choices. You either start with noise and using backpropagation you continue, or you initialize with the content image itself.
So why did you start with the noise image?
The point is, if you minimize that loss function, your image content should be very similar to content image and the style to the style image. But with noise, initially there is nothing. So after backpropagating the gradients to the noise itself, it becomes more and more similar to the content and style image.
So did you try both initializations?
Yeah,
They both work?
Actually, content works better, but other also the noise also works.
Okay. And then in my in the visualization notebook I showed yesterday, I had a animation that basically shows the development of the weights over different epochs. I bet you can do the same in this notebook and update your GitHub to do the same. So it would be interesting to see, for example, starting from a noise or gray image, how it evolves over epochs into the other image.
What
You
was
just-
the loss function? I couldn't get that one.
Sorry?
Your loss function.
Loss function. It's the mean squared error of the content representation of content image and the output image, the style representation minus the style representation of the output image, and there's a third regularization term.
Okay, I'll put pointers to his slides in the course website. I think it's done, right?
Here's the output. This one is the content image, this one is the style, and the middle one is the output.
What about the network structure?
It's VGG 16, but you can use other networks.
Okay. Let's thank our speaker. Okay, I have a much more boring topic today, but I think it's important. Optimization. This is something that we'll all have to deal with when we're training our models. So until now, I showed you how SGD works, and we made vague, we gave you vague hints about, oh, you know, if that doesn't work, play with the learning rate or use Adam or something. And in this lecture, I'm hoping to explain some of the ideas behind these more sophisticated optimization techniques. Before I get started on the theory, let me show you the reference. So in KNet reference, if you actually go to optimization methods, you'll see the update function that we use during training. And the update function takes weights and gradients. If you want to use a more sophisticated method than regular SGD, it also takes a third parameter called params. And this params parameter basically has the same size as the weights and the gradients, but instead of including weight matrices or vectors, it includes optimization structures. So for each weight matrix or vector in your model, there needs to be a corresponding struct which contains some statistics on the recent gradients, for example, for that weight component. So, and the structs can be initialized to represent different optimization algorithms. So we have 7 of them implemented right now: SGD, Momentum, Nestero, RMS-Prop, Adagrad, Adadelta, and Adam. Each of them have a learning rate and gradient clip option, but in addition, some of them have other parameters. Usually, default parameters work pretty well. And here's the typical usage examples. In the first one, we start with a random W, we calculate our gradients, and then the simplest call to update is just update W and gradients, which calls SGD with default parameters. You can also use the 2-parameter version with a learning rate keyword, which still does regular SGD with that learning rate. Or you can also use the 3-parameter version and explicitly supply SGD as the type of optimization you want to use, in which case it will do the same thing. So all these three commands actually do the same thing. If you want to use something more sophisticated than SGD, here's an example. So my model has two weight arrays, random D1 and random D2. These might be the weight vector and the bias of a linear model, for example. G becomes its gradient, which means G is also going to be a pair of arrays of the same size and shape that contain the gradients. Since I have two weight arrays, I need to initialize two optimization structures. So for the first array, I initialize an atom with default values, and for the second one, I initialize SGD. So that shows you that for different arrays in your model, you can use different optimization algorithms as well as different learning rates, different parameters, etc. And then I call update with all three variables. Instead of tuples, the next example uses any array. Otherwise, it's completely identical. You can also use dictionaries, which is not very efficient, but sometimes it makes the code a bit more readable. In that case, G also will become a dictionary with the same keys, and P, optimization parameters, also will become a dictionary with the same keys that point to optimization structs. Any questions about how to use this stuff in K-net? Not what they mean, we're going to cover that in the rest of the lecture, but how to call update and now one more useful thing I forgot, which is instead of hand initializing P like this, for more complicated models like VGG, this becomes very difficult, right? So VGG has tons and tons of different weights, and initializing a optimization parameter like this would become quite difficult. So I have a utility called optimizers, which basically takes a model, which is a list of weights or dictionary of weights or some other structure, and an optimizer type, for example, atom, and then it creates recursively, following your model, one optimization struct for each array in your model. So you don't have to do that manually. You can just call optimizers my model atom, and it will give you a bunch of little atom structures for every weight array. Okay. There's a notebook in the examples in the K-net repo under optimizers, which basically gives you the some usage and lets you test different optimization functions. You can actually look at the documentation for the different optimization types, and if you run it without any options, it tries SGD by default. I think it's optimizing Lenet, if I remember correctly. And if this notebook goes through every optimization algorithm and then calls the demo with that particular optimization algorithm, so you can see how fast each one converges, etc. Okay? So for usage information, you can also consult this example notebook. Okay, so let's see the theory behind numerical optimization now. So here's a rough overview. I'm going to try to get as much as possible through this. First, we're going to talk about, what is the difference between optimization and generalization? What does optimization mean for learning algorithms? And what are the difficulties that we need to take into account? We're going to look at gradient descent and look at the math behind gradient descent. So what is the optimal step size? What is the optimal direction to move when you're at a particular spot, and you can actually look at your first gradient, second gradient, etc. We're going to introduce a simple second order method called Newton's method, which is which takes first and second derivatives into account when it's calculating the ideal step. And then at the end, I'm going to talk about the different algorithms that are implemented in KNet. Okay, so first let's understand what we're optimizing exactly when we're doing machine learning. Okay, so you're going to say, of course, we're optimizing the loss function. Okay, but what does the loss function compute? What does it take as an input? It takes your parameters as input, and it takes x as input. What's x? Typically, it's a mini batch of data. Okay, so that means if I go to the next mini batch, I will see different data. Therefore, I will be computing a different function of w. Okay, so here is, so let's say I have w in 2 dimensions. These are my weights. Okay, this is the first weight, this is the second weight. And this particular graph shows me the loss function, loss w x, with, using the first mini batch for x. Okay. Now, I know that the ideal w is in there. I'm probably over here. I'm calculating some sort of gradient, and I'm taking a step toward the optimal value. Okay. Now, when I see the next mini batch, according to the next mini batch, this is what the loss function looks like in the w space. So every time you take a new mini batch, your loss function slightly shifts. So that means every time we're taking a step in the gradient of a different function. Okay, so that's one of the first things to understand about stochastic gradient descent. We're not optimizing a fixed function. The function keeps shifting underneath us because we're basically sampling these different mini batches. So backpropagation, the end goal of backpropagation is to minimize the loss on the whole training set. Okay? So in order to implement this efficiently, we use SGD, and SGD basically takes steps based on losses on individual mini batches. So that means the directions taken by SGD are noisy, because since I'm not seeing the whole training set, I don't know exactly what direction the gradient according to the whole training set would be. I'm just looking at the 100 samples in my mini batch. So that's a noisy estimate of the gradient direction according to the whole training set. Now, so that's basically considering the difference between a mini batch and the whole training set. Now, even the whole training set is not representative. In MNIST, we have 60,000 training examples. That's by no means close to covering all of the possible inputs in the input space, right? So typically our whole input space is, infinite. We have no access to the whole space. But what we really want to do is we really want to optimize the real loss with respect to the whole input space. For MNIST, the whole input space would be basically every 28 by 28 pixel image. Okay, so, and its size would be, if you're using integer pixel values, 255 to the power 784, right? So that's the number of possible images we can have. And I really want to optimize my loss function throughout that whole space, but obviously that's not possible, so I'm basically just looking at my training set. That's all I have labels for. And when I'm doing that, I'm also looking at individual mini batches when I'm taking my steps. So, because we're actually optimizing loss on a fixed finite size training set, we have overfitting. That's what causes overfitting. Overfitting means you're basically learning things specific to this data set rather than things that apply to the whole space of inputs. And how do we fight with overfitting? How do we detect overfitting? We detect overfitting using a validation or development set that we don't look at during parameter updates. So that held out validation set represents the rest of the input space for us. Okay? So we basically measure our performance on that, and that becomes an estimate of our future real loss on the future data points that we haven't seen yet. So now the difference between optimization and generalization comes into the picture. In optimization, in the topic of this lecture, we're only interested in optimizing the loss on the training set as quickly as possible. Okay? Generalization is the problem of how to close the gap between the training set loss and actually the real loss. Right? So that's another topic. So for the purpose of this lecture, I'm throwing away the test set, I'm throwing away the validation dev set. I'm only focusing on a fixed training set and how to optimize my function for that fixed training set. Okay? So, and this is a picture that sort of, summarizes the summary. Here's the ideal W for the whole input space. Here's the ideal W according to the training set. Here's the ideal W according to the dev set. And here's the ideal W with respect to the mini batch I'm looking at right now. They're all different. Okay? They're all trying to approximate one another, but just be aware that they're all different. 30 seconds for questions. Yeah.
About the mini batch size. So if I take bigger mini batches, it will be less noisy.
That's right.
So, yeah.
So why don't we take humongous mini batches, right? So even if your direction becomes less noisy, you still can't take a step that's really large because the space keeps twisting and turning. So the locally correct direction is not necessarily the correct direction in the long run. So that means if you're going to take a small step anyway, why are you worrying about calculating that direction exactly? Maybe an approximate direction would be just enough because after you take the step, the direction is going to change anyway. So it's a matter of using your computational resources efficiently. So typically, if you actually start changing your batch size and look at how long it takes, literally, real-time seconds, how long it takes to get to a particular loss value, you will see that there is a happy middle. If the mini batch size is too small, you're not making your GPU busy enough, so it's going to take a long time to converge. Your directions are too noisy. If you make it too large, then you're wasting a lot of computation to calculate a direction that's too precise, even though you're going to change your direction in the next step anyway. So there is usually a happy middle, and the happy middle depends both on your data set and your hardware, and you can experiment with that. I had a notebook doing this for MNIST, and the happy middle turns out to be somewhere between 100 and 1,000, for example. If you do less, it takes longer to converge. If you do more, it takes longer to converge.
Is there a convention like, let's say, 1% of the training set? It's good for me.
Training set sizes differ wildly, so I wouldn't actually express it as a percentage of the training set because MNIST has 60,000 examples, ImageNet has 1 million. Right? So if you base things on the training set, you may not hit the right number. So typically, with big problems, we basically decided on how much data we can fit on the GPU anyway, because after, you can't put more than 100 images on a GPU for training the ImageNet, for example. In smaller problems, you just experiment. Any other questions? Okay, so there is some terminology we should all agree on. F of x is our function we're trying to optimize. X star is the minimum that we're looking for. F prime I'm going to use as the derivative of f with respect to x, and if f prime is 0, then we call this a critical point. A critical point is where the gradient actually becomes 0. And this could be a minimum or maximum or a saddle point, and these could, the minimum or maximum could be local or global. Okay? All f prime equals 0 tells us is that locally the space is flat. So I could be here, I could be here, and I could be there. Okay? And in each of these three cases, if you're doing SGD, you would basically stop, right? if you were actually optimizing a fixed function, and if you reached any of these points, you would stop, whether or not these were the global optima or the local optima. Luckily, though, if you're doing SGD instead of doing regular gradient descent on the whole training set, you know this noise component. So next time you see a little noise, this minimum is going to slightly shift, and you're going to keep going. So because of that reason, SGD, for example, almost never gets stuck on a saddle point. Okay? So if you use more sophisticated and less noisy optimization algorithms, there is a chance that you will reach a saddle point, and you will have a hard time there. But since SGD keeps shifting this optimization function anyway, the objective function anyway, you just slide right down. Okay? Okay, so here's a very, very simple y equals x squared example. So the dotted line is my objective function. At x equals 0, I have a minimum. And I also have, this is a global minimum. My gradient is 0 here. Here's the solid line, shows my gradient. It's basically equal to x. For x smaller than 0, our gradient is negative. That means we're downward sloping. For x larger than 0, our gradient is positive. So that means we should go leftward. So this should be familiar to from your calculus class. Any questions here? Okay, so now, that was sort of all of these were for scalar functions. X was a number in the last two slides. Now let's make x a vector. So if x is a vector, I represent the vector here with a bold letter. So this represents a function with multiple inputs and a single output. So we go from r to the n to r. So that makes the derivative motion a bit more complicated. Now I have derivatives with respect to each of my inputs. So partial derivative of f with respect to xi gives me how much f would move if I actually move xi by epsilon. If I put all these partial derivatives into an array, I call that a gradient, and I represent it with this del character. So far so good? Okay, so next, let's talk about directional derivative. So directional derivative is basically, again, a single number, but I choose a direction. So I say, okay, here's the direction I want to move in. If I move in this direction by epsilon, how much is my function going to change? Okay, so u is the direction. U is the unit vector representing the direction I want to move into, and alpha is my step size, presumably a very small number. If I take an alpha step in the u direction, I claim that the resulting change, which is the directional derivative, resulting change in f, is going to be the dot product between u and the gradient of f. Can somebody tell me why?
Is it the projection on the gradient?
That's the projection of the gradient, correct. But why?
So basically, we want to calculate the change in the loss function.
Yes.
But so since the input is multidimensional, the change can be calculated like with respect to multiple directions.
That's correct. So a good way to visualize that is basically instead of saying, instead of thinking of a single step in the u direction, think of tiny little steps in the, the first component of u, in the x1 direction, in the x2 direction, in the x3 direction, right? So we're basically taking all these steps in the orthogonal unit directions that add up to u. Since everything is locally linear in calculus, we can add up the effects of these tiny little steps, right? So each of these tiny little steps is basically one component of u. If we wrote the vector u as an n component representation, u of 3 would be the third, how large the u is in the third direction. And if I go that amount in the third direction, how much does f change with that? Well, that's given by the third partial derivative in the gradient vector. So the dot product therefore expresses that. Should I draw this, or is this clear to everyone? Okay. So I'm going to draw it anyway. So here's my u vector, and it consists of u1, u2, dot, 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 un. And here's my gradient vector, and this is df dx1, df dx2, dot, 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 df dxn. So instead of thinking of moving alongside the u vector, I'm thinking of, okay, I'm going to first move u1 in the x direction, and that's going to give me this much, this times that change in my f. And I do that for every direction, and I add the results, and that's how I get the dot product. Now, the next claim is the ideal direction to move in, the direction that will give me the biggest bang for the buck. Okay, so if I travel in this direction by epsilon, I will get the biggest change in f. I claim that that direction is parallel to g. Why? So g is the direction that I can move in that maximizes the effect on f.
Since the dot product maximizes when the vectors are in the similar.
That's right. So I'm taking a dot product between u and the gradient vector, right? And as your friend suggested before, the dot product basically computes a projection, and this projection gets maximized if these two vectors are pointing in the same direction. Okay, we can also prove this using calculus and stuff, but so if you know that the best unit vector to dot product with a given gradient is basically the unit vector in the direction of the gradient, you can see that that maximizes the gradient direction, maximizes the effect on g. So that answers the question. If you were in a multidimensional space and if you wanted to move in a direction that would have the biggest impact on f, then you should choose the gradient direction. Okay? So if you move along the gradient, that increases f the most locally. If you move opposite, it decreases f locally. So that means we basically can write the gradient descent algorithm by saying every time we should compute the gradient of where we are and then just take a small step in that direction. Why a small step? Because gradient only tells us the direction that is locally maximizing the effect, right? So once you move a little bit, the gradient is different, the direction is different, so the place you want to move might be different. But yet still, that leaves the question, okay, I found the ideal direction to move locally. What is the ideal distance in that direction to move locally? So far, we haven't had a theoretical answer for this question. We just said, oh, let's call that the learning rate, and then just decide the learning rate by trial and error. Is there something that we can do that is actually better than guessing? So, what is the ideal step size? Now, this turns out to be an important problem, maybe one of the most important hyperparameter that you need to get right in order to make your optimization work. If you have the wrong learning rate, then you can needlessly take many, many steps to converge, which will take a lot of time. Or you can, if the step size is too big, you can become unstable and start bouncing around the minimum without ever actually reaching the minimum. Okay? So determining the right step size is the one of the most important problems. Okay, so in order to have a theoretical approach, we need to talk about second derivatives. Okay? Because if I'm on a flat surface, then the ideal step size is infinite, right? Because a flat surface never changes the direction. So if I find my local direction, that's always the right direction, and I should basically move as much as I can. What keeps me from doing that is the second derivative. So when I'm actually standing at an objective function at a certain point, there's a curvature. The curvature means the downhill slope is going to go on for a while, but then it's going to turn around. So that means if I take a step too big, I will hit the other side of this hole. Okay? So, and the second derivative is going to tell me how far the minimum of that hole is from me. So curvature, or also known as the second derivative, is the second derivative of f with respect to x. So let's start with a non-vector example again. X is a scalar, f is a regular function, r to r. So here's an example of negative curvature. The second derivative of f is negative in this case. Here it's flat, so the second derivative is 0. And this is positive curvature. This is how we hope our loss functions to usually be. Okay? So I'm standing here. I know I need to go in this direction. I'm just trying to decide how far to go. If I go too far, I'm not going to get a good result. I want to go this far to reach the minimum. So how can I calculate that step size if I know the first and second derivatives? Well, first of all, let's talk about what second derivative would mean in a vector function. So if f is a function of a vector, if x is a vector, that means there is not a unique number second derivative. Instead, there is a matrix of second derivatives. And this matrix is called the Hessian. And as you can see, it basically consists of partial derivatives of f with respect to any combination of xi, xj. Okay? And just like I can, in the scalar case, I can say, oh, my second derivative is positive, negative, or 0. Here I can say my matrix H is positive definite, negative definite, etc. So there is concepts in the matrix domain that are analogous to the concepts in the real number domain that I can apply. So if a positive second derivative in the scalar case is analogous to a positive definite matrix in the Hessian case. Okay? Any questions about the Hessian? Okay, so knowing the second derivatives is useful, as I will show you, in determining the right step size. So why don't our machine learning frameworks always compute the Hessian and work with the Hessian? Any ideas?
Very expensive.
So how many weights does VGG have? Roughly.
10 million.
10 million? Okay, so how large would be the Hessian for VGG? 10 million by 10 million. Okay, so it wouldn't even fit your memory, is the problem. So unless you have some sort of approximation, like only represent the diagonal of the Hessian or something, the Hessians are usually too expensive to work with in the types of problems we're interested in. Okay? Because our input has too many dimensions. But let's ignore that for a second, and let's say if we could work with the Hessian, then what would we do with it? Okay, sorry. I'm going to skip this. This is the Jacobian. Actually, I'm not going to skip this because this ends with a nice rhyme. Okay, so Jacobian is basically another matrix that should not be confused with the Hessian. And this is the matrix of first derivatives of a vector valued function. So input vector, output vector. So if the input and output are both vectors, then we have m by n different gradients for m inputs and n outputs, right? So the gradient of the partial derivative of the first output with respect to the first input, first output with respect to second input, etc. We can take m times n simple derivatives, and a matrix of these things is called the Jacobian. Okay? So these are first derivatives, not second derivatives. And then note that the Hessian is the Jacobian of the gradient. Okay? So that these three things that I just told you get combined this way. Why? The gradient is a vector valued function. Okay? So the input is a vector, the output is a vector of the same size. So therefore I can talk about the Jacobian of the gradient, which basically says, oh, what is the gradient of my first, the partial derivative of my first output with respect to the first input, etc. Right? But my first output is already a derivative. So what I'm talking about is second derivatives, and if you actually write this down, you'll see that that statement is true. Which is cute, we're not going to use it. Just know it. Okay, so let's talk about Hessians again. Things to know about Hessians. Hessians are usually symmetric. Why? Because derivative of f with respect to x1, x2 is the same as the derivative with respect to x2, x1. So it's a symmetric matrix. It's typically, we want it to be positive definite. It can be decomposed into eigenvalues and the corresponding eigenvectors. Yeah.
Did you say, you said usually symmetric because maybe complex matrices,
Yeah.
but we don't.
Yeah. Right now,
Space is
we're
not
not.
that way.
Yes. Correct. In the types of functions we're interested in, I think we can assume it's symmetric. So let's remember the eigenvectors and eigenvalues and what they are, and if you don't, ask me a question. So an eigenvector of something, eigenvalue, eigenvector, what does it mean? So if H is a matrix and U is one of its eigenvectors, then we know that that means multiplying U with this matrix is equivalent to, it does not change the direction. It just grows or shrinks the vector. Lambda is a scalar here, okay? So that's all you need to know about eigenvector and eigenvalue. Okay? So U transpose HU is the second derivative, is the directional second derivative in the direction of U. Okay? So we mentioned directional derivatives before, and this is basically talking about directional second derivatives. So if I'm interested in, for example, moving in the direction U, and if the second derivative basically tells me how fast this space is going to turn around and finish going down, then I need that number, U transpose HU. Okay? What is the size of U transpose HU? Dimensionality of the result?
Scalar.
It's a scalar, right? So it's going to give me a number that's positive or negative that basically tells me if I'm just looking at this part of the space, then what's the second derivative in that dimension? So this means that if U is an eigenvector, the second derivative is the eigenvalue, right? Because of what we said here. So if U is an eigenvector, then U transpose HU is going to be lambda U transpose U. And if U is a unit vector, this is just lambda. So in the eigenvector directions, the second derivatives are equal to my eigenvalues. Now, for a matrix n by n matrix like H, I have n, if it's a well-behaved matrix, I have n distinct eigenvalues. And these basically become my second derivatives in those special directions, right? What about intermediate directions? What kind of second derivatives can I expect in these intermediate directions that are not eigenvectors?
Linear combination of eigenvalues.
That's right. So every direction in this space can be written as a linear combination of eigenvectors, right? So that means the second derivative in that direction can be written as a linear combination of their eigenvalues. Okay? So So that means my second derivative is always going to be a weighted average of existing eigenvalues of H. So that means, for example, that it can never be more than the maximum eigenvalue or less than the minimum eigenvalue. My second derivatives are bounded by the maximum and minimum eigenvalues of H. So I'm taking weighted averages. Okay? Any questions so far? Okay, we're slowly coming to how far to step. All right. So let's say I take a step from x0 to x. Okay? So x0 is my starting point, x is the point that I move to, and if I write the Taylor expansion and try to approximate f of x, what f of x I will find, then the first order approximation says f of x should be the same as f of x0 plus however long this step was dot producted with g. Where did this come from? This is the dot producting of a particular direction with the gradient. And what did that give us? That gave us the directional derivative, right? So if I'm stepping in the x minus x0 direction, a certain distance, then the change I expect from the first derivative is going to be that step dot producted with the local gradient. That's the first order approximation. Any questions? Okay, so the first order approximation is no good though, because it doesn't tell me how far to step. If you just look at the first order approximation and try to calculate the step size would be infinite. As we said before, what's limiting your ideal step size is the second derivative, so we should look at the second order approximation. And the second order approximation for f of x, if you take the Taylor expansion, is going to look like this. After the first order, we also have this second order term, 1 over 2 x minus x0 h, etc. Okay? So this is the second order approximation of f. So any questions about the first two bullet points? Okay. So I'm usually talking about gradient descent or stochastic gradient descent in which the step direction I take is g or minus g, and I usually use a learning rate epsilon, so my updates look like x equals x0 minus epsilon g. Here x refers to my weights actually, so I should have called it w, but you understand. Okay. So my question is, if I'm going to step in the gradient direction or the opposite, how large a step should I take if I know the second derivatives, right? So if I'm stepping in the gradient direction, x is equal to that, right? And that means my second order approximation becomes epsilon g transpose g plus 1/2 epsilon square g transpose hg. I'm just substituting g wherever I see x minus x0, or epsilon g wherever I see x minus x0. Okay? And now I can say, okay, what's the ideal epsilon to use? And if you basically set this thing to take the derivative of this thing with respect to epsilon and set it to 0, we will tell you the best epsilon to use. And the best epsilon to use turns out to be this. Okay? So if you're stepping in the gradient direction, and if you're only using a second order approximation, the best step size, optimal step size is g transpose g divided by g transpose hg. So this assumes certain things like, h is positive, definite, etc. And of course it assumes that the second order approximation is good, so my function is locally quadratic. Okay? But under these assumptions, this gives us an idea. Now, let's play with this a little bit. What if g was one of my eigenvectors? One of the eigenvectors of h. Then I said g transpose hg would be just g transpose alpha g or lambda g, where lambda is the eigenvector. So the denominator and numerator would cancel, and I would just get 1 over lambda. Okay? So if I was actually looking at a eigen direction, then the ideal step size would be 1 over lambda. Remember, lambda is the curvature, the second derivative, the directional second derivative in that direction. So that means the smaller the second derivative, the larger the step I'm going to take, which makes sense because smaller second derivative means more flat surface, which allows me to take larger steps. A large second derivative means it's a very curvy space, so I need to take a small step because otherwise I'll hit the other wall. Okay? Make sense? And we should remember that G may not be the optimal direction to move. I'm just giving this as an example. So we can also ask ourselves, okay, if I'm going to move in the direction G, what's the ideal step size? But I could have also asked myself, what is the ideal direction to move if I just want to get the biggest decrease in F, right? And the answer could be some other direction than G. So now that we know how to calculate the ideal step size, which is basically 1 over the second derivative in the direction we're moving, let's go back and say what is the ideal step direction. We said, gradient was the best direction locally. That's true, but that doesn't necessarily mean a step in the gradient direction is going to give us the best improvement, especially if we know about the second derivatives. And here's an example. So this is a valley that's slowly going down. And if you're on the side of the valley or canyon, let's say canyon, okay, if you're on the side of the canyon, the gradient is going to point toward the other side, mostly, because you're basically facing a downhill thing. And you don't see that the bottom of this thing is slowly sloping downward and going really far, far away, right? So you're in this canyon, you're standing on one side, and the gradient is telling you to jump to the other side. Okay. So if you listen to the gradient, you're going to do a lot of jumping back and forth. But the actual direction you want to go in is this red direction, which is the river at the bottom of this canyon that's slowly going down. Yeah.
But if we tuned our step size well, we wouldn't be like bouncing. It would jump into the.
Well, first of all, yes, if you can actually manage to get to the bottom of this ravine, then you can basically do that. But usually these ravines are very sharp, so you rarely are able to hit the bottom. And as long as you don't hit the bottom, the sides will always give you the wrong direction. Okay? And here's an example. In this case, the eigenvectors are 1, 1, and 1, minus 1. Just points in this direction, right? And the 1, 1 direction, does the 1, 1 direction have higher or lower curvature? Those are the two directions. Is the 1, 1 direction high curvature or low curvature in this graph? Is it changing faster or slower? It's changing faster, so that means higher curvature, higher second derivative. In 1, minus 1, this direction is changing slower, so it has lower curvature, lower second derivative. Okay? In fact, in this case, the first eigenvalue is 5 times bigger than the second eigenvalue. So GD, gradient descent, basically takes those steps that that are marked up there, which, as you can see, has slightly large learning rate, so it keeps overshooting and going back and forth. And this is one of the problems that we want to avoid. So that means, okay, so this whole picture basically was to argue that the gradients may not be the directions that we want to move in. Okay? 30 seconds for questions. Yeah.
Do mini batching also have this?
Right, so mini batching, what sort of effect does mini batching have on this picture?
It changes the.
That's right. So the underlying geography keeps changing.
So it will not.
So yeah, that might actually help with the bouncing around a little bit. Okay. Okay, so Newton asked, after he invented calculus, if I was to take an ideal step, what is the direction and size of this ideal step? Okay, so let's answer both questions at once. What would be the ideal direction? What would be the ideal size? Assuming a second order approximation of my function. Okay, and I can do that by writing this thing down and taking the gradient with respect to my step and setting it to 0 and finding my ideal step. Okay? And it turns out the ideal step that we should take happens to be H inverse times G. Okay? Or minus that. So H inverse gives us the step size. Remember, if G was one of the eigenvectors, then Hg would have given us lambda. So H inverse G would have given us 1 over lambda, right? So that way it makes sense a little bit. The direction is not G, even though it's H inverse times G. H inverse is a linear operator, so when it multiplies a vector, if it's not an eigenvector, it's going to actually change its direction a little bit, right? So the direction is not necessarily G if we take that kind of step. But if it is an eigenvector, so for example, if you're in one of the axes of that ellipse, then it will actually be in the G direction. But if you're not on an axis, it's going to actually rotate the direction. And this step, H inverse times G, will go to the minimum of the function in a single step if the second order approximation was correct. Okay? So if I'm here at x0, my gradient is pointing in the green direction, but the Newton step is pointing in the red direction. So in the green direction, I need to take many small steps to get to the middle. In the red direction, I may need to take just 1 or 2 steps if it's a well-behaved function. So the ideal direction and size that we want to jump is given by H inverse G. Question?
Green one is GD.
Yes.
Maybe because of the mini batches, it chooses this path. No, it's not.
This is GD. In SGD we have mini batches. In
Ah,
GD
okay.
we don't have mini
GD we don't
batches.
have.
The function is fixed. Okay. So that means, well, how nice. So if we can repeatedly take Newton's steps, we can actually converge a lot faster than GD. Unfortunately, we can't do that in deep learning because the Hessian matrix is too big. So everybody has been obsessed with trying to approximate this and not pay the price of a 10 million by 10 million matrix. Okay, so how can you actually approximate the right direction and size without knowing the actual Hessian? Can you have some approximation of this Hessian somewhere? Can we do a diagonal approximation? And that's basically the source of all these different methods that you find in KNet, IMS-Proc, ADAM, AdaGrad, etc. They're all methods that basically try to approach this second order method without actually keeping around the huge matrix of Hessians. Okay. Another problem is if you have a fixed function that doesn't have SGD, so that doesn't have any noise, this kind of exactitude is sometimes harmful because it might actually find saddle points and get stuck in them. Okay? Newton is trying to get us to a critical point where the gradient is 0, and it might be too good and it might actually take us and get us stuck on a saddle point that we don't want. SGD does not have that problem. Or if we have add some noise, we can prevent that problem. Okay, so summary. We have a first order approximation, we have directional derivatives. If we take a step in a certain direction, then this is the type of result that we get, which makes the ideal step direction minus G and ideal step size infinite. And the actual gain, the change in F from the ideal step size is also infinite, but these are not realistic because they're just the first order approximations. 30 seconds for questions on this slide. Okay, here is the summary for the second order approximation. So now we have both f prime and f double prime. We still have directional derivatives u transpose g, and we also have directional second derivatives u transpose hu. Okay, so that gives us the gradient and curvature in any direction that we want to move in. So if we take a step in the direction u, then this is the fx that we're going to get, which, if you solve this equation, will give you an ideal step size and direction of minus h inverse g. And if you calculate how much f will change if we take this ideal direction, then you get this number, which is 1/2 g transpose h inverse g. Okay? So all of these things are things that you should be able to derive.
Is there any interpretation on the G transpose H inverse G?
Is there a?
Interpretation, what does it mean?
That's the standard second order term. So for example, if you're writing an equation with scalar values, a second order equation, you would say something like ax squared plus bx plus c, right? If this is a vector, then this would be x transpose hx, that would be the second order term. And then g times x plus some constant. So this type of term, a vector transpose a matrix, a vector, is a very, very standard term that basically just tells you it's a second, it's analogous to the ax squared term in a scalar function.
I have,
Yeah.
so in the Adam optimizer in a K-net package,
Uh-huh.
does it do something like calculating an absolute approximation for Hessian and applying also mini batching, because we do mini batching?
Yeah, we always do mini batching. What Adam and related methods do is they basically keep track of statistics on your recent gradients. Okay? So because the gradients keep changing, so they keep around first order and second order statistics on those gradients. And then instead of this H inverse, they basically use something based on the recent statistics of those gradients for each individual direction. And that could be interpreted possibly as a way of approximating a Hessian. Okay. Now, we said when gradients are zero, we call those points critical points, but critical points come in three flavors: minimums, maximums, and saddle points. And we can tell which one we're at by looking at the second derivative. If the second derivative is negative, it's a maximum. If it's positive, it's a minimum. If it's zero, then we don't know. It could be a saddle point like this, or we can be in the middle of a flat region. Okay? So same thing is true, analogous things are true in multiple dimensions. So a critical point is where the gradient is zero. And this time, to judge what kind of critical point we're at, we look at the Hessian for the second derivatives. If the Hessian is greater than zero, which means positive definite, which means all eigenvalues are positive for this Hessian, then we definitely know that we're at a local minimum. Okay, because whichever direction we turn into, we see a positive second derivative, which means this type of curvature, right? So that means I'm at the bottom of the bowl. If h is negative, definite, which means all eigenvalues are negative, then we're at a local maximum. Remember that every directional second derivative was a linear combination of eigenvalues of h. So if I have all positive eigenvalues, that means all second gradients in any direction are going to be positive. And same for negative. Okay? The third one is a bit different from the scalar case. If I have at least one positive eigenvalue and one negative eigenvalue, then I'm at a saddle point. Okay? And if I have a 0 lambda, and all non-zero lambda share the same sign, I don't know where I'm at, okay? Because according to some directions I'm flat, according to other directions I might be positive or negative. And if you actually generate random functions, you know, you will see that, or random Hessians, you will see that saddle points are exponentially more common in higher dimensional spaces. So most of the critical points that we find in a very, very high dimensional space, like with 10 million weights, are going to be saddle points. They're not going to be minimum or maximum. Okay? So you definitely want a method which does not get stuck on saddle points. And SGD is great because it's all shaking and stuff anyway, so you never get stuck in saddle points with SGD. Questions? Okay.
Why do saddle points are more? Because they need minimums and maximums.
If you generate a random H, which means the eigen values of these things are also randomly generated, then most of the time you're not going to get all positive eigenvalues or all negative eigenvalues, right? So that means most of the time you're going to get positive and negatives, which will put you on a saddle point. You can think about it that way. I'm sure there is a better mathematical explanation in the book.
Maybe we might think of it like if we have a million eigenvalues,
Yeah.
it's harder to get like all of them positive, right?
Yeah.
Because it's 1 over 2.
Yeah, if you're actually, you know, doing it by flipping the coin. But what I'm not sure about is whether the coin flipping analogy is accurate in this case. So, as I mentioned before, back when I was learning about neural networks the first time in 1989 or something, this is the problem that our professor told us that neural networks had: local minima. Okay? Since neural network objective functions are usually non-convex, they have multiple critical points, some saddle, some local minima, etc. And they said, oh, your space is full of these things, and you know, you might be actually converging to this point, which has a higher loss, where actually better loss values are available. Okay? However, it is true that neural networks have tons of local minima. Why? At the very least, look at the weight symmetries. If I have an MLP with, let's say, 64 hidden units, I can rotate and permute these 64 hidden units any way I want, and I have the exact same neural network. So each of these permutations basically give me a point with an equivalent neural network in the weight space. So just because of these symmetries, I have tons and tons of local minima. But is that the really important problem? So one of the most educational examples for me was from some work we did on machine translation a couple of years ago, where we tried initializing a Turkish-English machine translation model from the weights of a French-English machine translation model. Okay, so instead of starting with random weights, why don't we start with some other language's weights that was trained on a larger data set and had better results. And this was the result we had. So let me explain this. So the solid line is the training curve without the transfer. Okay? And this small dotted line is the training curve with the transfer. Okay? So as you can see, the transfer case actually optimizes a lot faster, right? It converges a lot faster. But also note, they converge to exactly the same loss. So at the end, the loss on the training set is the same, whether or not you initialize it randomly or you initialize it from French. Okay? However, there is a big difference in the validation set values, right? So even though the training set performances are identical, the model which was initialized with the French numbers actually converged to a loss very close to the training loss, whereas the randomly initialized model converges to something that's much worse. Okay, so what's this telling us? Number one, this tells us that these two models are very, very different from each other. They converge to very, very different places in the weight space. However, these two very different places have the exact same loss. What this means is that this space is full of local minima, or maybe basins, other geographic regions, I don't know what the shape looks like exactly, of local minima, which pretty much all have the same loss value on the training set. Okay? So you start from different places and you basically end up at the same loss, but you're in a different position. So my possibly inaccurate picture that I have is basically I imagine a large tray. Okay, so I have mountains surrounding a flat middle region, and wherever you start on the edge, you basically drop down, and as soon as you hit the flat region, you stop. Okay, so I'm sure that's not how it looks like it, but that's one way to imagine it. So the French guy starts from here and hits this spot. The randomly initialized guy starts from here and hits this spot. They're all at the same height, but they're very, very different weight-wise. And somehow, the guy who started with the French weights generalizes a lot better, which means that this region actually is a lot nicer in terms of generalization. Okay? So specific to this training set, these two weights appear to be equal. But if I actually imagine the whole space, then the French initialized version generalizes a lot better. So, what's the result we can get from this? The result we can get from this is, first of all, this was not the main problem. Because I have zillions of local minima, but it doesn't matter because they're all equally good according to the training set loss. Okay? So the problem is not I'm at a local minima and not a global minima. The problem is that I'm at a minima which is equal to all its other minima, siblings, but this minima does not generalize too well. Okay? So that's typically the problem we have with our modern over-parameterized neural networks.
Can I ask a question?
Yeah.
Was there any reason that the French initializer give better development error? What was that?
Yeah, development loss
Yeah.
was better.
Was
Well,
there
if
reason?
you, I can give you anecdotal reasons. I don't know a theoretical reason, but basically my rule of thumb is if you can, initializing your network randomly is the worst possible thing you can do.
But at the end you have the same loss for both of them.
That's true, but the other guy actually has learned a lot of stuff from French. Remember, they're both translating from English. So the whole English part of the network was already good. It probably retained a lot of that information into the Turkish translation. It already knew how to represent English sentences as a vector at the end of the encoder or an, for example. All that information was still useful, right? Now, my little randomly initialized Turkish guy also had to learn to represent English sentences from scratch, but it did so looking at much less data because I have much smaller Turkish English data. So it wasn't very good. It found some way to map English sentences to vectors, but it probably wasn't very good. Whereas the other guy actually had, about 100 times more data, and it was able to arrive at a solution that generalized better.
And can it be like the transferring the part of the transforming English words to vectors and not transferring the weights of transferring the English vectors to French? Because we are transferring.
Yes, we actually experimented with a bunch of different settings where we froze some of the parameters and we trained some of the parameters, so you don't, because we knew some of the model would want to change drastically. The Turkish and French parts are not very similar to each other. but the English part would probably try to stay the same, so we experimented with freezing different parts of the model. Okay, last picture I'm going to show you, last few pictures is, again, pointing out that this picture is wrong, which is in a Goodfellow article. What Goodfellow did is basically, let's say you're training MNIST. You start at a random initial point, you're at a high loss, 2 point something, and then you train this thing until you arrive at a, maybe 100 epochs, and you're finally, at the minimum loss. And if you keep training, maybe it doesn't, Now, you know the starting initial point in the weight space, you know the minimum in the weight space, you can draw a line between them, and you can basically pick 100 points in that line to see how the loss changes along that line. Okay? So if I was in a space riddled with local minima, then I'd expect to see a curve like this. Well, this is the curve he gets. So that's the, this is the initial point, this is the minimal point, and the blue curve represents the training loss interpolated at points interpolated between these 2 points. So if I actually took a straight line, if somebody told me that this is the direction where the minimum is, and if I took a straight line and kept moving in that direction, as you can see, my loss would be decreasing very smoothly. Okay? The reason I had to spend 100 epochs is I don't know what this direction is. So there is no blocks in that direction that's preventing me from reaching the minimum, other than the fact that there is a lot of other directions and I'm all confused and the gradient points over there and I don't know exactly where the minimum is in this big space. Okay, so that's the problem, rather than the local minimum. So here is the interpolation between two solutions. So at 0 there is a solution, at 1 there is another solution. And as you can see, in the middle it goes up a little bit. But again, as you keep away from the solutions, the weights slowly rise up. From a random starting point, it looks like a very, very smooth function. Should be very, very easy to optimize. But again, it takes 100 epochs because the space is very high dimensional. And finally, this is a 2D picture of what the space looks like for an artificial problem. So here, dark blue means minimum and red means maximum. The arrows actually show you the gradients. Okay? And it's a very simple network with two weights. And as you can see, even in this network, there is not a single spot where there is a single minimum. Instead, there is a critical point right here, which is a saddle. And there's a bunch of critical points around this green, which are all the same, at the same loss. And there's a bunch of them over here, which again are all at the same loss. And if you start something like this, somewhere like this, the gradient descent would take you in this direction. And the low, if you actually were able to go straight to the closest minima, you would go in this direction. Okay? So any questions about these pictures? So I highly recommend this Goodfellow 2015 article if you want to get some intuition as to what's happening in your optimization space. All right, so we'll have an exam on Thursday in class.
Do you have anything to say about the content?
Whatever we did in the lectures and the labs. I put a sample midterm from previous years. Ignore the KNet examples because that's KNet version 6 or 7, which was very different from the version we're using right now. But you'll get the rough idea of what kinds of questions there will be. No, because I just did it today, so optimization not included.